Hello, Physics Nation. My name is Nate Larmond, and hopefully you've built this apparatus. There's a whole video series on how to chop up circles and make this little hamburger down here. These inside circles are just a little bit smaller than the outside circles. This looks like it's 6 plies thick. And, the goal is to hang this off the edge of your desk or table so that the pencil, the little wheel and axle spins freely. The annoying part of this project is the vertical supports. These holes have to be lined up and it has to be anchored firmly to some kind of base. So I just used my kids' blocks to stack up the vertical members temporarily. So this is my little scaffolding. And then I put a bunch of gussets in here. Crafting glue is great, dries really fast. Doesn't really matter if you're sloppy because even those things a mess, oh, there you go. It still works. Okay, so that's what we're shooting for. And at first, we're just going to define kinematics. We're just going to measure how far it goes, how long it takes, the average velocity, the final velocity, and the acceleration of our little toy car here. So weight hangs off the end, and then that weight pulls on your low friction car. Calculations are pretty simple. Pardon the scrolling here. Release it from rest, so there is no initial velocity. And, average velocity equals displacement over time. Well, it also equals the initial plus the final velocity divided by 2. So we're going to use these two mathematical relationships. You simply put a starting line and a finish line. Remember, when the weight hits the ground, it stops accelerating. So you actually want your finish line before this weight hits the ground. The starting line is as far back as possible. I mean, the bigger the distance, the more accurate your time is going to be. So, 3, 2, 1, bang, and then stop it when your car gets to your finish line. If you have displacement in time and there's no initial velocity, displacement divided by time is the average velocity, and then you just multiply the average velocity by 2 to get the final velocity. Here is a graphical representation of what's happening to the velocity. Once you let go of that car, it's going to gain velocity at a constant rate. Hopefully you made your, pulley an effective machine. Pulleys transfer force. It changes a downwards force into a horizontal force. Anyway, the velocity should grow at a constant rate, and here's the average velocity. Well, that's halfway through the acceleration. If you double that, you get the final velocity. And then what we're going to do is find the acceleration, that is the rate of change of motion. So you just take the final velocity, subtract nothing, there is no initial velocity, and divide by the time again. And that's the rate of change of motion, otherwise known as the acceleration. And we're actually going to see what things will affect the rate of change of motion, the acceleration. So what if you put more and more mass, like 2 nickels, 6 nickels, 10 nickels? Coins are a very standardized mass. You can use them as mass standards at home. What's going to happen to all of these kinematic variables? Some won't change. Displacement, for example, is set by your little starting line and finish line. What's going to happen to the time? There is no initial velocity, so that's not going to change. What's going to happen to the average velocity, the final velocity, the acceleration, as you stack more and more coins on this little Hot Wheels car? I'll leave that up to you. Have fun experimenting. See you in the next video.